Okay, guys, so of course we're supposed to be up to chapter 3 by now, which is spanning tree protocol. And so basically spanning tree protocol is to stop switching loops. Now, the reason that you need this special protocol for layer 2 devices is that there is no part in the header that actually has keeps account of how many hops that a frame has been through, and so basically there's no way to know if this frame has been bouncing around. There's no timing or anything like that to know that this frame has been bouncing around for the last 20 hours in a continual loop. And yeah, so basically back in the 80s they developed spanning tree protocol to prevent loops, but of course it allows you to have redundant links in case primary links fail, and so you can still have some redundancy and reliability. And so, you know, I've got this packet tracer here and 3 switches in a loop, and as you can see, one of those links has been disabled, so that if a host sends out a broadcast, it won't bounce around the network forever and kill the network, basically. I have actually had a broadcast loop at home. If you got those, you know, the cheapy switches that you get at home, they do not run spanning tree protocol. I learned that the hard way. I assumed if they were a layer 2 device they would, but apparently not. So what I had was I had a central switch. It was just one of those, you know, cheapy little things that you have, and I had a wireless access point hanging off of it as well, and I had a spare cable hanging off the wireless access point, so if anyone brought a computer and they wanted to hook it in to a wired connection, that's what it was for. And I think one of my sons actually decided, oh, there's a loose end to a wire here, I'll plug that into the switch. And so I actually had 2 links between the same switch and the wireless access points, so I had a loop. And then the family was complaining, I can't get in the internet. And so, yeah, so I did discover it. I can't remember how long it took. It was a few years ago now, thankfully. So they are real, they can happen. But of course, with your business level switches, they run spanning tree protocol, and so they're a lot less likely to happen. So if we look at the configuration for the switch, looking at the CLI, now one thing I've done is, some people have complained about the visibility of these, and so I've actually upped the font size on this. So probably one of the things I should do is widen it, because 10-point font takes a little more room. And so you can actually do show spanning tree, and this will show you the settings. And so I've done this on switch 1, which is the one that is root by default, and it's convenient enough to tell you that this bridge is the root. And so you basically get the details of the root bridge, which is sort of the center of the topology. And so you get its priority as well as its, so basically add the priority to the address, and that's the bridge ID. And so that's, this is the root bridge's details. And of course, this is the bridge we're sitting at's details. And of course, because this is the root bridge, it's the same details. And so it also tells you the timing settings for STP as it's running. So hello time is every 2 seconds. There's that is the hello packet. And then if after 20 seconds we stop getting hello packets from a particular bridge, that is when we assume that the bridge is down. And then the forwarding delay time is 15 seconds. And so there's forwarding, and then there's learning and then forwarding delay. So you actually get that 15 seconds twice. And that's probably why you've heard of 50 seconds delay, is your 20 seconds age plus 2 times by 15, so it equals 30. And so that's why spanning tree protocol can take 50 seconds to come back good. And so there are only 3 active ports, which are the 2 interswitch links as well as the host port. And so the host is on fast Ethernet, Now, one of the major types of ports that we talk about in STP is a root port, but of course the root bridge itself doesn't have any root ports because it doesn't need to go through a port to get to the root bridge. And so that's how it looks on the switch by default. If we do show running, the spanning tree settings are pretty much up the top of the switch there as well. And so you can see that the spanning tree mode is per VLAN spanning tree. So that's what Cisco uses by default. And also there's the setting for the extended system ID version for the priority. And so I think if we scroll up a bit here, it actually explains how that works here. And so the priority is 32,768. And then the VLAN ID is actually, that's what is used as extended. Part of that priority setting is VLAN ID, and the other part, of course, is your waiting. And so those two added together is actually what sets that there. And so this is just again, the default settings. Nothing has been done to reconfigure that. And so that's basically as it comes out of the box. And so there's nothing else there of interest as far as spanning tree is concerned. So if we look at one of the other switches, again, CLI, widen it, so EN show spanning tree, and we have very similar information, but of course, so because we use per VLAN spanning tree, you can actually get a whole pile of entries for all the different VLANs that are running. Of course, this is default, so there's only VLAN 1. And so as you can see, the root ID is this, which would have been exactly the same as what we looked at the other previous switch. But of course, this one isn't the bridge, and so this is its own details. So as you can see, the priority is the same because they haven't been played with yet. So it's only because the other one has a much lower MAC address is the reason that it actually is the root bridge. And so you can see it's a fair bit lower by this. And so again, we've got the timing information. So here, the major difference is that we have a root port because this is not the root bridge. And so that is the port that we use to get to the root. So of course, the fast Ethernet's got the host in it. And this is a designated port, which means it's there. It hasn't been disabled, but the other end it has. So if we look at this other switch, EN show spanning. And so again, default priority for this one, which is the same as the root bridges, it's just its MAC address, it's different. But the port types are different. And so you'll see that this gigabit G01, which I'm assuming is this one here, is what's called an alternate port. So it's not active at the moment, but if there were to be a topology change, it could possibly come up. And so you'll see that it's in blocking mode because it's not active at the moment. So if we look at this other one, I don't think any of, see, they were all in forwarding mode there. And so that is the port that is disabled. And so no loop, all very happy. Now, what can we do with spanning tree? So over to this notepad that I've got here. And so, of course, we saw this in the configuration. Spanning tree mode PVST is the standard per VLAN spanning tree. Now, that's, of course, actually, if we look back at this, it might have actually said IEEE. So basically, it's just, that's the original version of spanning tree is IEEE, Institute of Electronic Engineers. So if you wish to have rapid spanning tree running, you just need to change the mode to rapid-PVST. And so that will turn that on. Now, to play around with which switch is root and so on, there are more than one way to do that. So if you do the iOS gives you this functionality of spanning tree VLAN 1 root primary. And so basically that's saying I would like this to be the switch that becomes root typically. While there is the other option of doing root secondary. And so what the line I've got below is actually what ends up in the configuration if you do that. And so it sets its priority to be, roughly 24,000 as opposed to the 36,000 it was before for primary, and it makes it 28,000 to make it secondary. And so, of course, this is normally where you're, this is somewhere in the region of where they would normally be. And so that gives you a comparison there. And so what I might do, I might actually do all of these commands on a different switch to the one that normally becomes root. And so you'll notice I've got the exclamation marks there. That just treats it as a comment, so it actually ignores that line. So now if we do show spanning, now switch 3 is the root bridge. Now, of course, we're busy recalculating routes at the moment. So actually what I might do, I might fast forward time to get it all to finish. And you'll notice that instead of this port being deactivated, now it's this one. So I'll go back to that. Is it switch 3? Yes. Now I might actually run the command again, now that it's all up to date. And you'll notice that now the protocol running is RSTP, not that IEEE version. And you'll notice that even though I typed in root primary, it ended up being very much the same as that. But of course, it is, of course, the priority of 576, like I said, plus, of course, the VLAN ID of 1. And that's why it ends up being 24,577. So the timings haven't changed, but of course, now this is the root bridge. It doesn't have any root ports. Now let's make this one the secondary. Copy, paste, and so we've put it into a rapid spanning tree, and I'll just run this command as well. And show spanning. And as you can see, this was the original root, but now that we've played around, it's got a priority that's 28,000, while that switch 3 now has a priority of 24,000, and so it is the one that is the root bridge. Might have to do that command again. All the ports seem to be blocking at the moment. That's not what we want. Oh, I want switch 1, not switch 2. That's a bit better. The previous one actually hadn't decided on its root bridge yet. Because I'd changed it to rapid spanning tree, it was still calculating basically. So that's better. And so the root bridge of root port, of course, is G0/1, which I'm assuming is this port here. And it is. And so the other ports are designated ports, which means they're active, but they're not the route to the root bridge. And so on switch 2, we basically just need this command. Might as well have them all running the same version of spanning tree. And so, of course, okay, Seems to have sorted itself out. And so we have G0/1, which is the root bridge, and we have G0/2 as being the alternate one that's blocked. So 1 is that one, and 2 is that one. So that's all good. Now, if we look at, one thing we haven't done is look at the show run and see what extra lines have gone in there. And so now we've got it in rapid per VLAN spanning tree mode, and we've, as you can see, that's how the priority ended up going. I did the root primary, but it calculated what the priority should be itself. And so I use that root primary and root secondary all the time because it's just easier. It's a computer, it does maths quicker than I do. So I let it do it. And so that's basically how you play around with it. Now, I suppose there is further complication once you start adding extra VLANs. Now, of course, if we added a VLAN 2 and had this one as the root, you would actually not see any of the, get off of that. You would not see any of those yellow ports. So basically the beauty of it is if you have this one as being the root for VLAN 1 and this one for VLAN 2, then all the VLAN 2 traffic would go across this link and all the VLAN 1 traffic would go across this link. And so you can actually balance your traffic across different links. But of course, you still have that redundancy available if one of those links were to fail. And so that's why Cisco goes to the trouble of doing per VLAN spanning tree, is to enable you to do that kind of balancing and trying to optimize your traffic. Now there's another thing that we speak about in that chapter, and that is basically port fast. Now port fast basically is a way to speed up ports that don't actually need spanning tree to run, and so you don't get that 50-second delay. So I'm going to say let's hook another host into a port as a bit of a demo. Plug it in there, plug it in there, and we're going to have to wait 50 seconds basically. So spanning tree, okay, spanning tree's figured out that it's a edge port. Let's have another look at that. It's figured out it's a point-to-point link, so there's no other switches there. So it's actually come up quicker because of RSTP, basically. But you can actually do this, and it was yellow for a little time. If we do this on the ports, now, of course, we normally put the port into access mode. I'm using the interface range command just so I don't have to do all 24 ports individually. And when you do port fast, you actually get a warning. And so because I'm doing it for 24 ports, it will have actually given me 24 warnings for each of the ports. And so when it has a warning, it actually says port fast has been configured on the port, but will only have effect when the interface is in a non-trunking mode. Port fast should only be enabled on ports connected to a single host, connecting hubs, concentrators, switches, bridges, etc. to this interface. When port fast is enabled, can cause temporary bridging loops. Use with caution. And so that's the message you get each time. And so on 24 ports. So if we do a show running now, you'll notice that each port has that switch port mode access and port fast on it. So now if we throw another host in and plug a cable in, straight to green, no pause at all. Let's do show spanning tree again. Has anyone noticed the costs? This is fast Ethernet, so it has a cost of 19. Because this is gigabit Ethernet, it has a cost of 4. And that's actually how it calculates what is the best route from a switch to the root bridge. So were there any questions on that? Is that pretty much understandable? Now, next chapter, we actually look at HSRP, which is Hot Standby Routing Protocol, as well as Ether Channel. And so basically, you can use Hot Standby Routing Protocol to have alternate spare routers, basically. So standby routing protocol, so you can actually have more than one local gateway. So it's a local gateway redundancy protocol. And so that's, and using that in combination with per VLAN spanning tree can be very advantageous to you for using your links. And then also we look at Ether Channel. And so with Ether Channel, you can actually have multiple links between switches, and normally one of those links will be disabled. But with Ether Channel, it actually treats it as one link. And so it combines multiple links together to actually get your, so you can up your bandwidth. But if one of the physical links fails, whatever ones are left will still continue to work. So it has some advantages in that as well. So it does sort of the topic does intermingle with one another. So that's why we're doing it. So that's pretty much it, the spanning tree. That's all we were going to do, basically. No other questions at all? All seems relatively understandable, does it? So I might just save this, and I'll put it up on the Cisco server so you can have a look.